Hi, this is our third video on equilibrium, and we are going to start solving equilibrium problems. Now, we're just going to dive right in and get started. So here we have an equation that is an equilibrium, and they give us a value for the equilibrium constant K. So the K is 170. So that is telling us that equilibrium lies to the right because K is larger than 1. Now, one thing that should have been specified in this problem is that these values here are at equilibrium. So the concentration of the hydrogen and the nitrogen at equilibrium are given to you. And they would like to know the concentration of ammonia at equilibrium. So what I suggest is that first of all, you set up a K expression. So K is equal to our product, which is the ammonia concentration, and that's what we're trying to solve for. And it's squared because of that coefficient in the balanced equation, divided by our nitrogen concentration at equilibrium that was given to us, times the hydrogen concentration at equilibrium that was given to us cubed. So in a K expression, all these concentrations have to be equilibrium concentrations. Well, our value of K was 170, and then that's equal to, well, we don't know what ammonia's concentration is, so that is X, and it has to be squared. The nitrogen concentration is 6.00 times 10 to the negative 2, and the hydrogen concentration at equilibrium is 5.6 times 10 to the negative 2. And because of the coefficient in that balanced equation, we have to cube it. So what we do here is we do 6 times 10 to the negative second times 5.6 times 10 to the negative second cubed times 170 will equal X squared. And so when you do that on your calculator, and I would stop the video and make sure that you're getting the answers that I'm getting to make sure that you're inputting all of this into your calculator correctly. When I do that, X squared is 0.00179. And then the value for X, which is the ammonia concentration at equilibrium, is 0.0423 molar. Okay, so in the past, they've given you all the concentrations at equilibrium and asked you to solve for K. Here they gave you K, gave you all but one of the concentrations at equilibrium, and you solved for it. So nothing really new. All right, but now we're going to do something a little bit new. We're going to look at this system at equilibrium. A is in equilibrium with B. They're going to give us a K. They always give us a temperature because K changes with temperature. And they're giving us initial concentrations, not equilibrium concentrations. So that's different. And they're asking for the equilibrium concentrations. All right, so let's see how we're going to do this. So the first thing that we're going to do is let's start with our balanced equation. A in equilibrium with B. The K for this value is 24 at this particular temperature. And we're going to set up an ice box. I stands for initial, C stands for change, and E stands for equilibrium. So take a minute and write that down. Initial, change, equilibrium. They give us the initial concentration of A, and we want our concentrations to be molar, and it was 0.850 molar. They don't tell us anything about the initial concentration of B, and so that means that it's 0. Now, as this reaction goes, because there is nothing over here, it has to be proceeding from left to right. So we have to be making B. And we're depleting A until we get to a state of equilibrium where it's 0.850 minus X for A's concentration and X for B's concentration. Okay. So what we're going to do now is we're going to write our equilibrium expression. K is equal to the concentration of B over the concentration of A. And these concentrations are the equilibrium concentrations. All right, so K, 24, concentration of B at equilibrium is X. The concentration of A at equilibrium is 0.850 minus X. So what we do now is we solve for X. When we get X, that will be B's concentration at equilibrium. And if we subtract X from 0.85, that will be A's concentration at equilibrium. All right, so when I went ahead, so you may want to stop this and solve for X. The X value that I get is 0.816. Okay. So when I do that algebra, I get a value of X of 0.816. So that is the concentration for B at equilibrium. And then the concentration of A at equilibrium will be 0.850 minus 0.816. And when I do that, I get A's concentration to be 0.034 molar. Now let's see if these numbers make sense. B's concentration at equilibrium is 0.816 molar, and A's concentration has gone down to 0.034 molar. Well, our K is bigger than 1. It's 24. And so that means that equilibrium favors the concentrations on the product side. Is the product concentration higher than the reactant concentration? It is. So the final answer here is the concentration of B at equilibrium is 0.816 molar, and the final concentration of A at equilibrium is 0.034 molar. So let's take a minute and talk about these steps. You need a balanced equation. The equilibrium concentration is always specified in molarity. So make sure that you use molarity. And we've got an initial concentration. I use X for the change in concentration. And then we have an equilibrium line. I also suggest always writing a K expression. And then you plug in your values. Okay, so this question is going to have some coefficients in it. So we've got a K, and we've got a synthesis reaction, and now they're telling us that they're putting 1 mole of each reactant into a 10-liter reaction vessel, and they want the equilibrium concentrations of everything. All right, first of all, we need molarity for our concentrations. So it says here, if 1 mole of each reactant is put into a 10-liter vessel. So that means, remember, molarity is moles over liters. Each reactant's concentration at the beginning is 0.1 molar. So we had to change that moles to molarity. All right, here's what we're going to do. We're going to go to a new slide, and we're going to write ourselves a balanced equation. So our balanced equation is H2, it's a synthesis reaction, plus I2 is an equilibrium with 2 HI, and the K for this is 57. Again, we're going to expect to have a higher concentration of products than reactants at equilibrium, and we're going to make ourselves an ice box. Initially, there was 0.10 molar of the hydrogen and of the iodide. Nothing was mentioned about having any of this in here, so it's 0. So the change line is minus X because we are depleting this and we are making this, and you bring down the coefficient, plus 2X. And so at equilibrium, we've got 2X and we've got 0.1 minus X and 0.1 minus X. All right, K is equal to the concentration of HI squared divided by the concentration of H2, I2, and this is all at equilibrium. So K, 57, is equal to 2X squared divided by 0.10 minus X times 0.1 minus X. So I'm just going to say 0.1 minus X squared. Now to solve this, I'm going to take the square root of both sides. and I'm going to get the square root of 57, which is 7 something, I think. Yes, 7.55 is equal to 2x divided by 0.1 minus x. All right, now we're going to cross multiply, divide by 2, and when I'm all done and I have solved for x, and maybe you're going to want to take a moment to do that. I'm not going to do all the math on this screen. I get x being 0.0791 molar. Now the question was, what are the equilibrium concentrations of everything? So for HI, the equilibrium concentration is 2, wow, that's a weird 2, times 0.0741. So that is 0.158 molar. And the concentration of hydrogen at equilibrium equals the concentration of the iodide at equilibrium, and that is 0.1 minus oh my goodness gracious. It's 0.1 minus 0.0741, the x, and so that answer is 0.0209. So I've kind of run out of room to write here. All right, so hopefully you got all that written down. I would actually stop the video and retry this problem and see if you're understanding the icebox. Okay, here is, I think, our last problem, and it is at 450 degrees, and it's a decomposition of ammonia, and they're placing 2.25 moles of ammonia in a 3-liter container, and they're heating it, and then they're telling us how many moles of ammonia we have at equilibrium. They would like us to find the concentration of everything at equilibrium and calculate the value of K. So here we go. Here I'm going to give myself more room here. Here's our equation. Ammonia is decomposing into nitrogen and hydrogen gas. So balancing the equation, I think that'll do it. All right, now they tell us initially the amount of ammonia that we have is so many moles, and then it's in a 3-liter container. And so to get the molarity, I take those moles and I divide it by 3, and I get the concentration of 0.75 molar. We don't have any products at the beginning. Minus 2x, so this is our icebox. And then at equilibrium, and this is an x and this is a 3x. At equilibrium, they tell us the amount that we have at equilibrium. They tell us the moles. We divide by 3 to get the molarity of 0.174 molar. Remember, these equilibrium expressions have to be in molarity, so keep your table in moles per liter. All right, and now we're ready to solve for K. So K is nitrogen times hydrogen cubed divided by ammonia squared. Well, we can figure out x from this right here. So 0.75 minus 2x is equal to 0.174. So x is equal to 0.288. All right, so at equilibrium, that is nitrogen's concentration, and then 3 times that will be hydrogen's concentration. So hydrogen's concentration is 3 times 0.288, and we get hydrogen's concentration to be 0.864. All right, we've got the concentration of our nitrogen, of our hydrogen, and of our ammonia. We plug them into this expression. Don't forget to cube and don't forget to square ammonia. And when I solve for the value of K, I got 6.14. All right, have a good night.